Greetings everyone. Today we are about to review on the topic Raman spectroscopy, a study of ancient South African domestic clay pottery.
Without further ado, allow us to introduce the background of the study. In this work, selected South African earthenware samples have been investigated. These materials were in the form of domestic clay pottery shards. Basically, they belong to the low-temperature fired ceramics or clay pottery. In this study, the determination of the main components of these materials were carried out through Raman spectroscopy. So generally, this study aims to analyze the chemical composition of the samples through the detected Raman spectra. In this way, the raw materials used in the samples can be determined and so the processes involved. Hence, the success of this investigation would then contribute to the advancements in the application of Raman spectroscopy in characterizing earthenware materials and revealing their production methods, notably in South Africa. Next up is a theoretical background. As per the researchers, the technique of Raman spectroscopy was used to examine a series of African domestic clay pottery shards. Such a detailed examination of pottery could give valuable information and a characterization of archaeological items by the identification of materials such as pigments, binders, and clays used in the manufacturing process. In fact, the importance of this subject has already been demonstrated in the literature. Moreover, the chemical composition can be used to define the pottery of a particular area and people by determining the raw materials used. And for very important artifacts, the knowledge of the composition of raw materials and processing methods used will help in the reconstruction of such pieces. Now, in terms of the sintering processes, there are two ways in which the pottery could be fired: in an open fire and in a kiln. The open firing methods have an upper limit of 800 degrees Celsius, while the kilns could reach a maximum temperature of 1230 degrees Celsius. In addition, there are a number of techniques known to analyze pottery for defining non-local pottery, such as XRD, trace elemental analysis, spectroscopy, etc. However, the clay-based chemical and mineralogical analysis are said to be complicated due to the diversity of the clay minerals and trace elements in nature. Further, tempering or plastic agents in the pottery are often well suited for use as indicators of provenance and origin, even though they could be traded. The plastics are often used to retain the shape of the pottery, controlling the shrinkage during drying and firing processes. In fact, many tempering agents are not good indicators in source area, such as that of bone and shells, because they are common, but rock fragments and sand grain are better due to the fact that they may reflect the geological source. Now, let us proceed to the materials and equipment used in the experiment. But firstly, the experiment was conducted on the samples originated from four areas in South Africa, namely Lydenburg, which is shown in Figure 1, Makahin in Figure 2, Graskop in Figure 3, and Reewal in Figure 4. Now, here are the instruments used in the following characterization techniques. But we have to say that the images shown in Figures 5 to 8 were not really taken from the paper under review. So, as for the Raman spectroscopy analysis, the Dialer XY Raman spectrometer was used, accompanied by an Argon Coherent Innova 300 laser, an Olympus BH-2 microscope, and with the help of LabSpec version 2.04 software. For X-ray powder diffractometry or XRD analysis, the Siemens DIV-501 with a graphite secondary monochromator and a scintillation counter detector was used, such that was shown in Figure 6. Whereas shown in Figure 7 is the instrument used for the infrared spectroscopy analysis, which is the Bruker 113V FTIR spectrometer. On the other hand, an ARL 9400XP plus wavelength dispersive XRF spectrometer with a rhodium source was used for the X-ray fluorescence analysis of the samples.
And now, let us proceed to the methodology, results and discussion, and conclusion. The Raman spectroscopy was performed at a room temperature. In the experiment, the following parameters were used: 2 cm to the -1 power of resolution, radiation at 514.5 nanometer, 100 megawatts of laser power, between 30 and 180 seconds of recording time with 2 accumulations per spectrum segment. Then the Raman spectra were analyzed using a software. And for XRD analysis, the following parameters were used: 1.5418 angstrom, a source of 40 kilovolts, 40 milliamperes, and at 30 RPM, the powdered samples were rotated on a plastic plate. For infrared spectroscopy, the following parameters were used: 400 to 4000 cm to the -1 power, spectral solution of 2 cm to the -1 power. This investigation was carried out to all samples. Lastly is the X-ray fluorescence. For XRF analysis, the samples were dried and fired at 100 degrees Celsius in such a way that the LOI, or lost on ignition, can be determined. The analysis of major elements on fused beads were based on the methodology used by a university adapted from Bennett and Oliver as cited in this paper. On the other hand, the analysis on trace elements on pressed powder samples were based on the methods employed by Watson. Results and discussion. Leidenberg sample number 8 in Figures 5, Makahin sample number 7 in Figure 6, Graskop sample number 5 in Figure 7, and Royal sample were the representative shards. For all the samples, the obtained spectra were characterized mainly by the presence of aluminosilicates, inorganic phases, and pigments. The typical Raman spectra of samples are shown in Figures 5 to 8 for their wave number range of 150 to 1700 cm to the -1. While the Raman assignments of phases in the samples are summarized in Table 1 in the next slides. Considerable amounts of hematite, quartz, feldspar, kaolin, montmorilonite, elite, and calcium silicate can be observed through this data. In Figures 5 and 6, the bands at around 220, 280, and 405 cm to the -1 are said to be due to red iron oxide, and the presence of this reddish area throughout the sample and in the bulk of the body could be an indication that this pigment was one of the starting material. Meanwhile, the XRF results revealed a relatively high content of hematite, which is around greater than or equal to 7 mass percentage in Figures 7 and 8. The Raman bands at around 460 cm to the -1 are due to quartz. These bands are typically very intense and narrow when quartz is in its free and isolated form. The appearance of kaolin clay mineral throughout the Raman spectroscopic analysis of samples suggests that the processing temperature was insufficient. This is critical to allow the complete dissolution of this clay mineral. Also, the Raman spectroscopy results confirm the complexity of clay minerals in which features resembling elite clay mineral are shown. In fact, the broad and intense band might be preceded by an overlapping of quartz and elite bands. Meanwhile, the presence of Montmorillonite clay mineral is relevant to the bands around 310 and 830 cm to the -1. Hence, the firing temperatures of below 850 degrees Celsius is confirmed due to the presence of these clay minerals, since they are known to initially break down at around 850 degrees Celsius. The bands that are associated with calcite further confirms a low firing range. The fact that the calcite is naturally occurring at shells and limestone is an indication that it occurs as an impurity in clays. Weak features previously associated with non-crystalline calcium carbonate at 695 and 724 cm to the -1, shown in the FTIR spectrum. The presence of feldspars was also conveyed in Raman bands around 511 cm to the -1 and through the XRD results. The presence of amorphous carbon was implied throughout the intense bands at 1358 and 1576 cm to the -1. This phase is most likely bone black for its corresponding peak at around 970 cm to the -1. Anhydrite phase was also implied in the Raman bands. In XRF, residual SO3 was detected, but as expected, this anhydrite phase was not shown through XRD results. Moreover, Leidenberg, McCahane, and Graskop were found to exhibit the gypsum phase as suggested by the Raman bands around 680 and 1007 cm to the -1. And finally, a summary of all the chemical phases identified by Raman spectroscopy in all representative samples was presented in Table 5.
Conclusions. So, based on the results, the Raman spectroscopy technique has been carried out successfully in determining the composition of African clay pottery shards from the selected archaeological sites. There were a total of 13 chemical phases in the samples identified by Raman spectroscopy. The fact that this technique has revealed considerable number of chemical compounds in low-temperature fired clay products infers its high sensitivity and applicability to this sort of materials. The commonality in features of the representative shards were observed. Hence, the clay minerals in pottery making process employed to these materials might have not varied significantly within the said region. Overall, through this study, the Raman spectroscopy has demonstrated a significant ability in detecting various chemical species in low-fired clay products, implying its functionality in determining the raw materials utilized, processing conditions, and discrimination based on the unique chemical compounds. So that brings us to the end of the presentation. Thank you so much for your interest and attention.